Okay, this is part two. In part one, we looked at Kerf, what it was, and we looked at the different compensation methods. At least it's in Fusion 360, but as I mentioned, you'll have to compensate in your other cam codes as well. I'm just not sure how they do it. But we looked at the sideways and the compensation, which included right, left, and center. With center really not being a compensation, went directly along the lines of your anticipated design. But we also said that, hey, if I can use that center, the fact that it's not doing any kind of compensation, and if I make a cut, I ought to be able to determine then what my true kerf is. And it's probably different than what's in your cut charts, and we'll see in fact that that's the case. So this is part two, just continuation on, and this is where it gets some interesting. We see some results of test data and get some more information about how to determine what your true kerf is. Okay, so let's go on to the part two. Thanks.
Part of what we want to do in this video is determine what our true kerf is. And so we've postulated that we can do a cut and find out what the actual measurement is and subtract that from what the design measurement was, and the difference would be our true cut. So if we select that center compensation, which again doesn't compensate at all, runs directly along the design path, and so in this particular case I'm saying let's use this little coupon, 2 inches on the side with a 1 inch diameter circle, and we'll focus in on the circle part. And so we want to cut this 1 inch diameter. Well, we'll cut it out and we measure what the actual diameter says. So I'm going to claim that the true kerf is the desired, which is the 1 inch, minus the actual, and that value then becomes our true kerf. Now note that that kerf value is valid only for the material that we've cut. This being 11 gauge, if I was going to use that kerf on 1/4 inch, then obviously that's not right. And obviously, it's also depends on whether that maybe a fine cut or a normal cut, consumables. I'm sure, although we won't test that, but if you consumables are wearing, your kerf is probably changing. There's a number of variables, cut height, your speed, etc., that may affect your kerf. So whatever you measure here is only going to be for that particular variables combinations. I don't know how much your wearing of your consumables changes kerf, but I would think that it's not a whole lot, but I could be wrong there, and maybe if someone knows different, they can let me know. Well, that gives you the actual kerf, and we're claiming that that's the kerf that you should use in your kerf settings to get a good dimension. If it's not, you may still have to do some tweaking and adjusting that kerf to increase or decrease what that value actually is.
Okay, let's talk about some of the things we've done experimenting to understand what the effective kerf value is, number one, and the secondary desire was to see if we could use this to come up with what our actual kerf is, using our idea that the design dimension minus the actual dimension would give us that answer. What we've got here are 9 coupons that I've cut out. These coupons were pretty much one of the coupons that I used back in that bevel video. I use this same design, which is it's 2 inch square, so it's 2 inches on a side, with the middle circle being a 1 inch diameter. And what you've got here on the top row is a kerf dimension of 0.023. The middle row is 0.056, which is what the book calls for, and the bottom row is 0.079. And so the top row is half of what the book calls for. The bottom row is that half added to what the book calls for. In the columns, column on the left is, I've chosen the sideways compensation left. The one in the middle is a sideways compensation of center, and the right one is the right sideways compensation. Now we're going to be looking at some test data, so I wanted to show you where that data came from.
So with each of these coupons, in the center hole, you know, in our plasma table, oftentimes it doesn't cut an exact circle. And so I've taken a number of measurements along that circle and I've averaged them out. And then you'll see a height dimension, just simply a height and a width dimension. And so in the center, those should be pretty close to an inch if everything was right. And height and width should both be the same, which should be 2 inches. Okay, let's look at the results of the test where we've cut out those 9 coupons that were 2 inches on a side square and with a 1 inch diameter circle in the middle, and have measured those. And remember, they were cut with different kerf diameters or kerf settings and different sideways comp, left, center, and right. And here's now the results of that data. And you remember on the inside diameter, we took an average, and so we've now listed that. Here's the 3 different kerf settings, with the 56 thousandths being what the book essentially called for, and the 23 being half of that, and 79 being a half of what it was called for added to it. So 23 thousandths plus 56. And so it's broken up in each of these. Here's a diameter, here's a width, here's the height, and in each one there's a left comp, a center comp, and a right comp in each of those measurements. And this is a tabular value of that. For me, it's a little easier to see what that is visually. So let me pull you down here, and we're going to look at what the chart says. There's a couple things I want to point out. Obviously, here we see red is the right compensation. This whole is all for center. I'm sorry. So we're just now talking about that inner diameter circle, the 1 inch diameter circle we're trying to cut. We'll do the sides in the next chart. And so right compensation is red line, left compensation is the black line, and blue is the center. You'll also notice that each one of them has a dashed line where I have just taken a linear extrapolation to see where that would intercept this vertical axis, and we'll see why I want to do that here in a second. I'll also note that I've got this dashed line right here. It should also go all the way up to the center line. This is the value that came using the 56 thousandths kerf value that came out of the cut chart. There are some interesting conclusions that you could take off of this chart. Notice that here's the center line. Remember, center, there is no compensation. So whatever you measure from that cut using center line, you can almost look at this and say, okay, what is this? Well, that says that it's 1.020, which is 20 thousandths over what you wanted, which is 1 inch. So that would suggest that the kerf is, about 20 thousandths of an inch. But can we get that also from the left and right? Well, again, when we've extrapolated these out, if I look at this 1 inch value, here's what I wanted. And I come over here and find out where that intersects those and come down and look. That basically says that if my kerf value was 14 thousandths of an inch, I would wind up with a diameter of 1. If I use left or right. Well, so there's a difference. That says use 14, this says use 20 thousandths. And so we will investigate that a little bit farther. So that was the inside circle. Let's now move on to the outer part, the square height and width. And here again are the test results. We're going to focus here on this area. And as just in the circle, when we look at the center, when we've chosen center sideways comp, which really isn't any comp at all, those should pretty much be the same no matter what your kerf is, because it's not adjusted, it's not compensating for kerf. And sure enough, when we look at center, those are real close to being the same, off by, I don't know, a couple thousandths of an inch, and center. However, let's look down here at the chart data. It's a little easier to visualize. And notice that the red is using right sideways compensation, and it's the height measurement. And the green here is right compensation using the width measurement. Red and black are left compensation values. And then again down here, the blue and I guess that's another red, are the center. And those should be pretty much close to the same. Notice that the green and red have the most variation. I don't know exactly what's causing that. I'm trying to convince myself that what's causing that is this idea that the jet has a good cut side and a bad cut side. And when you're moving in the left compensation default direction, which is counterclockwise for inside cuts and clockwise for outside cuts, it's my understanding that that's trying to keep the good side of that plasma jet on, making the cut, on the cut path. Whereas in right, where it reverses that direction, I'm wondering whether that's putting the bad side of the cut now on that cut line. And so is that what's causing this amount of variation? I don't know. That's my guess. I don't really know for sure. If someone knows and has some, better answers on that, let me know. All right, so we're back to trying to see if where we should be in order to achieve the desired 2-inch diameter or 2-inch measurement, 2-inch on a side. And you can see no matter where we are on left or right, we're still outside of that 2. So if we get larger kerf, it's not good. 56 thousandths, which is the book calls out, it's not good. It doesn't get close to 2 until we get down into this area, which looks like it's about, 22, 23 thousandths. I mean, this is 23 right here, and those all seem to be converging down around that area. So about 23,000 might be the right thing. Notice also that just like when we were looking at the diameter, that 1-inch diameter circle, that we can look at the values for center and get some sort of an idea of what our kerf is. So if we were to extrapolate these out and look at where those basically are going to wind up, although they seem to be going in opposite direction, but if we took an average there, that's basically saying if I wanted 2-inch, what I'm actually seeing there is 20 thousandths difference. So it's saying that my kerf is about 20 thousandths of an inch. Well, that's basically the same thing I'm saying here. If I wanted to and find out where the best kerf was setting to get me to, well, that's about the same thing, 22 thousandths of an inch. So both of those seem to be pointing to the same value of kerf. So now that we have all that data, let's go back to what we postulated, is that we could take the center cut, center sideways compensation selection and take the difference between our desired cut and our actual dimensions and come up with true kerf. So in here we say, okay, we're going to take the cut dimension minus the design dimension, and that value, now we're going to absolute it because one could be larger than the other, you wind up with a negative value. We're going to ignore all that. We're just going to take the value as a positive and see what happens. So if we look at the inside diameter center line, we see that the difference between that 1 inch that we wanted and what we actually achieved was, if you average those out, maybe that's 16.5 thousandths. On the width and the height, if we do that same thing, in this particular case, taking the desired dimension of 2-inch, minus what we actually achieved, these are the differences. And we say, well, on average, there's probably about 25 thousandths. In this particular case, probably, I guess the average is also 25 thousandths. Now, here's a little bit of a dilemma. For our inside cut, our, quote, true kerf using this method wound up being about 16, 17 thousandths of an inch. Whereas if our outside cut, wound up that we should be using 25 thousandths of an inch. What do? Well, I guess my guess would be that, if you're cutting a hole that maybe you got to get a bolt through or something like that, well, then you would use the kerf that gave you the best dimension for an inside cut. Whereas if you're trying to cut out a puzzle piece that had to fit into something, so your outside dimension had to be right, well, then you'd lean on using the outside dimension cut. I guess, you can't have both, although any of these is significantly different and will give you a better measurement than what the book called for. Now, while I was trying to figure out how to get to kerf, I thought there was an easier way. If we took for each material and its intended setting, the feet per minute, whether it's a fine or regular consumable, etc., and we did a straight line cut using our Langmuir capability, and you cut for about 3 inches, and then you simply use a feeler gauge down through that cut line. Isn't that the true kerf? I can't convince myself that it wouldn't be, and so we're actually going to try and test that and see what the effect is. See if we get any correct answers. So what you're going to see next is some videos of the cuts. After I was done cutting all these different materials, I had to obviously take the dross off, clean up both sides, and then come up with what that measure was. You're going to see that it's different depending on if you're on the torch side or you're on the back side. And this goes back to our bevel issue. And so now trying to decide, do I, try and figure out what the torch side is and use that as my measurement, or do I use the back side, which is the actual, what I can get a feeler gauge through? And you'll see the difference here in some of the data. Okay, here goes, we're going to try 1/4 inch and see what we can measure as the kerf. We'll get a feeler gauge, we're going to see what that is. Here we go with 3/16 inch. Next is 11 gauge. I'm cutting this at 175 inches per minute. Next is 16 gauge. We're cutting this at 250 inches per minute. Final cut here is on 22 gauge, and although the book would call out 325 inches per minute, our little machine won't go that fast, so I'm set it for 299 on the straight cut. Quarter inch. Here is our 3/16. Here's our 11 gauge, 16 gauge, and 22 gauge. I'm gonna get all these off the table, clean the dross off the back so that it doesn't affect the measurement, and then we'll measure each one with a feeler gauge and see what we got. I've got these lined up in order at the torch side, showing from left side being 1/4 inch, the right side being 22 gauge, and you can get an idea what the size is. Here now I've flipped them over, still 1/4 inch on the left side, the right side is the 22 gauge, but you're looking now at the back side after they've been cleaned, the dross has been cleaned off, and you get an idea of how much smaller the back side is than it was on the torch side. One of the problems of doing this straight line cut method to determining kerf is that the torch side and the back side are significantly different. And so when you're trying to measure, if I measure the where the gauge just starts to go into that slot, which should be this torch side, I measure, that totals up to be about 61 thousandths of an inch. Whereas if I turn this thing over and we look at the back side, it's significantly smaller. You can tell just by looking at it. And in fact, it winds up being where the feeler gauge that goes through is about 37 thousandths of an inch. So the difference being on one side would be 60 thousandths, on the back side being 37 thousandths, it's significantly different. And so you say, well, which one should I use? Well, in our other method where we took that circle and then we measured the inside diameter of that circle, this size difference is due to the bevel. Obviously, on the torch side, it's wider than it is on the back side, and that's due to that bevel issue that often we have with the plasma torch. When you're measuring that inside diameter, the bevel's there, so you are measuring the inside or the smallest part due to that bevel. So you're really measuring the smallest of the hole. So we should be using whatever feeler gauge will go through the entire thing instead of trying to figure out what feeler gauge goes in part of it on the torch side, which is pretty subjective. All right, so here is the data. I did 5 different material sizes from 1/4 inch down to 22 gauge. And here's the value that the cut chart said I should be using. Here is the value measured on the torch side versus the back side. And you'll notice when you look at the difference between torch side and back side, you can see there's a big difference. It's like half. And it's not until you get down to the thin material, which obviously doesn't have much room to bevel, that you get close to the same values. Here's what those look like in the chart. And there's a couple things of interest. So these values, even though they're not labeled, this is 1/4 inch, 3/16, there's your 11 gauge, 16 gauge, and here's down to that thin 22 gauge. You can see that the cut chart values right here and the torch side values and the rear side values all are significantly different. So this raises the question again of what should I use? Should I use the torch side value for my quote true kerf? Should I use the rear side value for my true kerf? Let's look at the 11 gauge, which we have data for in our 9 coupons, and see what that is. Well, here's the value that was used out of the cut charts. Here's the 56 thousandths. But the torch side was smaller than that. The torch side wound up being, about, well, let's see, over here, 11 gauge, 48 thousandths. And the back side being 22 thousandths. Well, you recall when we measured that on the sides, our height and width, it was pretty close to 22 thousandths. And I'm thinking that a straight line cut is comparable to our side cuts center line measurements, center measurements. And so sure enough, this is saying the same thing, that we're 22 thousandths. So I'm thinking this is kind of validation that this is also another way you get your true kerf measurement. But what it doesn't allow you to do is know if I want to get a certain dimension, do I increase my kerf or do I lower my kerf, and by how much? So let's go back to this method, and in particular our circle center dimension. And if I could take and do this for each of the material that I wanted to cut, I think it would be very useful. And here's why. Let's say again I'm trying to create an inside diameter of an accurate dimension. Let's say the 1 inch. I can take from here and go and say, well, where did that 1 inch occur? And I can come down and say, oh, you know, my kerf needs to be 14 thousandths of an inch. Now, let's say I did the cut and I said, oh, dadgummit, it's, you know, it's low. It's less than 1 inch. Well, what do I need to do to go make it larger than 1 inch? Well, I need to go in this direction. So that would mean I would need to decrease my kerf value. Or let's say that it's still too large and I need to reduce that diameter. Well, I know that I need to come back in this direction, and so I need to increase my kerf value. So what this chart does for me is allows me to know what direction I should go in order to get the actual dimension of where I want to be. I don't know if the user, the YouTube viewer that wrote to me and said that he was using Kerf to get his dimensions correct. I don't know how he did it, whether he modified his Kerf and took a look and, you know, kind of tweaked it, or if he had some methodology that allowed him to know how much to change to get the right dimension. But regardless, this is, I think, would be helpful for me. It just means that I've got for every combination of consumables and materials that I'd have to go and do this cut. And I may actually do that for some of the things I do normal cuts with. I do a lot of 11 gauge, 16 gauge. So at least for those two, I've already got the 11 here. If I do 16 now, that might be of usefulness. Well, I hope that long discussion was useful. It helped me because it gave me some ideas on how to tell what that true kerf is, and probably incorporate that in some of my cuts in the future when dimensional accuracy becomes critical. So appreciate you watching. If you got any comments, let me know. If you've got some other areas of our plasma tables or some questions you might have, throw them my way. I don't know if I can answer them, but maybe it'll turn into an interesting video. Okay, thanks for watching.